In this video, we will be discussing the electronic geometries as proposed by the valence shell electron pair repulsion theory. When you have two electron groups that are around the central atom, they will attempt to occupy positions on opposite sides of the central atom. This results in the electron groups taking on a linear geometry in which the bond angle is 180 degrees. Examples of this are beryllium chloride and carbon dioxide. It doesn't matter whether it is a single bond or a double bond, electron groups count the same. So for carbon dioxide, you have one electron group here, one electron group here, or if we are looking at the Lewis structure, an electron group to the right of the carbon, one electron group to the left of the carbon. And so because the central carbon atom has two electron groups, two different locations where you can find electrons around it, it takes on a linear geometry. If we expand this by one, when there are three electron groups around the central atom, they will occupy the positions in the shape of a triangle around the central atom. The resulting electron group takes on a trigonal planar geometry, in which the bond angle is 120 degrees apart. An example of this is boron trifluoride, BF3, drawn out in an example of a Lewis structure. You have a bond between the boron and the fluoride here, as well as here and here. So around the boron, there are three electron groups. What this looks like three-dimensionally is the entire molecule lies along a plane, and the groups, the fluorine atoms, occupy points on a triangle. So because everything is in a plane and the shape forms a triangle, this is called trigonal planar. Next, when there are four electron groups around the central atom, they will occupy the positions in the shape of a tetrahedron around the central atom, where the shape of the tetrahedron comes from faces or planes that are made by three of the atoms that are bound to the central atom. So you would have a face from these three hydrogens, and then a face from these three hydrogens in the back, and then another one on the left from these three, and then the final plane of the tetrahedron would be along the bottom from these three. This results in an electron group taking on a tetrahedral geometry. So the name of this particular geometry is tetrahedral. The bond angles are 109.5 degrees, and that is between any two hydrogens and having the carbon at the vertex of the angle. When there are five electron groups around the central atom, they will occupy a position in the shape of two tetrahedra that are sitting base to base with the central atom in the center of the two shared bases. So you would have a tetrahedron, a four-sided object on top, and a tetrahedron on the bottom. This results in the electron group taking on a trigonal bipyramidal geometry. The reason for this name is that the base of each pyramid, so the pyramid is your tetrahedron, so up, down, this would be one pyramid. The base of it forms a triangle. So it is trigonal bipyramidal because there's a pyramid on the top and a pyramid on the bottom. The positions above and below the central atom are called the axial positions. So this is axial, this is axial. Those that are in alignment with the central atom are called equatorial positions. Those are at 90-degree angles from the axial positions. So each one of these three is at a 90-degree angle from your top axial and also at a 90-degree angle from your bottom axial. The angle between the equatorial positions is 120 degrees. The positions in the same base plane as the central atom, these three here, are called your equatorial positions. Finally, when there are six electron groups around the central atom, they will occupy positions in the shape of two square-based pyramids that are base to base with the central atom in the center. So you would have two pyramids, one on top between this fluorine in this example, this fluorine, this fluorine, this one, and this one. Going up, that would make one pyramid on top, one on the bottom, and they share this square on the bottom. This results in an electron group taking on an octahedral geometry. The reason that it's called octahedron is because the figure has 8 sides. The geometric figure itself has 8 sides. Each side is made up of a plane that touches 3 of, in this case, fluorine atoms, or 3 of the atoms that are attached to your central atom. So here is one plane, another plane, it comes from these 3, another plane from the one on top and the 2 in the back, and another plane from the one on the top and the 2 on the left-hand side. Similarly, there will be 4 planes that come from the bottom. In the octahedral geometry, all positions are equivalent, and the bond angle between any 2 adjacent fluorines is going to be 90 degrees. The bond angle between fluorines that are on opposite sides of the central atom would be 180. But all the other bond angles will be 90 degrees apart.